people. Okay, this will be the final one for day 2, the 2D geometry, if you've actually gotten this far. Okay, let's go ahead and get started. Again, this is circle 1. I went ahead and cheated again and pre-drew the circle. I'm okay with drawing circles on the whiteboard, but for some odd reason when it's a piece of paper on the table, I have a problem. So, after a rupture, oil begins to escape from an underwater well. If, as oil rises, it forms a circular slick whose radius increases at a rate of 0.42 feet per minute, hate decimals, find the rate at which the area of the spill is increasing when the radius is 120 feet. Okay, so we are given certain information. That information is the fact that the radius is increasing, right? And it's increasing, dr dt, at a rate of positive 0.42 feet per minute. I need to identify the question. The question is, find the rate at which the area of the spill is increasing. So that is dA dt. And you need to find that when, what happens when I'm writing and speaking at the same time, when the radius is 120 feet. So when r is equal to 120 feet. Okay, well this is a pretty straightforward one. This is much like the last one that we did, or at least part of it, because that one was a 4-part problem. We simply need to remember that area is equal to pi r squared, right? And dA dt is equal to 2 pi times r times dr dt. And now we simply just need to plug in the numbers that we receive, the values. So it's 2 pi, and my conditional information, at that moment in time, the radius is 120 feet, and at that, it's always increasing, because that was the given piece of information, at 0.42 feet per minute. Now, if you were to go ahead and turn 0.42 into a fraction, which would make me happy, if you want to go play with decimals, go to physics. You know, they do that in science. But basically, if you were to try to represent this as an exact value, it'd be 504 pi over 5 feet per minute. But the way that approximates is 316.673 feet per minute. Remember, always approximating to 3 decimal places, and always writing a cute little sentence which shows that you understand what's going on, right? Okay, now I told you that we're going to have a distance problem that was a little bit easier. Well, it's a little bit easier because it's not trig. It does have its own complexity because it's a sideways parabola. I went ahead and provided the graph for you on this one, but let's go ahead and read it. An object is moving along the parabola. Okay, so that means that basically, kind of like they said in the last one, a particle is moving along the curve, right? So basically just imagine a dot just sort of traveling along the curve. An object is moving along the parabola when the object is at the point. So when the object is at that point, so that's your conditional information. That's basically saying when x is equal to -1 and when y is equal to 4. Its y-coordinate is increasing at the rate 3 units per second. Okay, so the given information, you kind of go, I don't know, is there any given information? It kind of sounds like that rate that we're given right there is part of the conditional, but it doesn't really matter. We're going to plug it in nonetheless, so we'll go ahead and just leave it down here with the conditional. But it's asking how fast is the distance from the object to the origin. So again, it's going to be origin to your xy coordinate. So it's looking for, and this time let's use z for it. So it's, what is dz dt? We'll use z as the distance variable, and the conditional. And remember, like we did in the previous one, the distance formula is just Pythagorean Theorem in disguise. So if your conditional is -1, and if your conditional is x is equal to -1 and y is equal to 4, and z is the hypotenuse of those two, then z has to be root 17. right? Just think about it. You're thinking about this point right down here. Like that is the moment in time that you're talking about. Well, it has, basically you can draw a right triangle to there, 1, 4, and of course this is the square root of 1 squared plus 4 squared, which is the square root of 17. But we also have the fact that dy dt at that moment is 3 units per second. Okay, well that's kind of neat. The next thing we're going to need to do, obviously, is if we're going to be dealing with the distance formula, we need two ordered pairs, right? Well, this right here is y squared is equal to 3 minus x. We're not going to be able to isolate y. Well, I mean, I guess we could, but if we did that for the bottom half of the parabola, there would be square roots involved, and I really don't want to deal with that. Now, in the past, when we had y equals, some expression in terms of x, we would go ahead and designate the variable as x f of x, right? X, comma, and then whatever expression is set equal to y or f of x in that y coordinate. Well, here's the thing. We're just going to do the opposite here. We're going to basically derive an ordered pair in terms of y. Well, that makes sense because we want the equation in terms of y. We don't want it in terms of x because we have dy dt right here. We don't have dx dt. So let's go ahead, and this is y squared over 4 is equal to 3 minus x, or x minus 3 is equal to negative y squared over 4, or x is equal to 3 minus y squared over 4. That means that if x is 3 minus y squared over 4, and y can just be y. So here's our ordered pair, and of course, since we're looking for the distance from the origin, our second ordered pair is 0, 0. Now, again, we're not going to use the square root. We're going to go ahead and say the distance from the distance squared is equal to, and again, remember it's minus 0, so it winds up being 3 minus y squared over 4 squared plus y squared. Okay, well let's differentiate. And when we differentiate with respect to t, remember that all three of those terms are going to have a 2 in them. So let's just go ahead and leave that 2 out. Let's just differentiate and divide through by 2 in one fell swoop. And we get 3 minus y squared over 4 times, of course, now we need to deal with the derivative of the inside. That's negative 1/4 y squared. It becomes negative 1/4 y dy dt plus 2y, sorry, the 2 isn't supposed to be there. We already decided we were going to get rid of it, y dy dt. Okay, well, let's go ahead and clean up this left-hand side. We are looking for dz dt, so we'll go ahead and clean up this right-hand side and then either divide by z or multiply by 1 over z. Now, this is two terms right here, both of which have a dy dt. Now, when I distribute this negative 1/4 y across here, I basically can use the negative to flip the difference, and I get 1/8. No, sorry, this is supposed to be 1/2 y. Sorry. This is going to be y cubed over 8 minus 3/2 y, but then I'm going to have a plus y. So that's actually, I'm going to go ahead and do the work for you and let you know that it simplifies to that. And if you need to take a second, pause the video and work it out for yourself and verify that. And then I'm just going to multiply by 1 over z. Okay, well, let's go ahead and plug in. Okay, we have dz dt, we have dy, no, we're looking for dz dt, we have dy dt, we have y, and we have z. Okay, so dy dt at that moment is 3 units, I'm just going to use u because I'm 3 units per second, okay, and then y, well, y is 4. 4 cubed is 64, 64 divided by 8 is 8. If y is 4, then 1/2 of 4 is 2, so it's 8 minus 2. And then z over here is 1 over root 17, right? Because it's the reciprocal of z. Now, And what we need to do here is, I mean, this had units and this was over units. So the reason there are no units of units, that sounds so bizarre, is that they cancel out in these two because this one is divided by that one. But if I simplify, this is 3, this is 6, I'm going to get 18 over root 17 units per second. And that, in case you're interested, actually approximates to 4.366 units per second. And then you would just write me a nice cute little sentence that explains that you understand what that means. Okay, last problem. We're going to deal with something that's, it should be relatively straightforward, but of course it has a little wrinkle to it. The vertices of a rectangle are 0, 0, 0 e to the x, x 0, and x e to the x. Okay, well, let's just pretend that we're on the Cartesian plane, shall we? 0, 0 is easy enough, right? That right there is 0, 0. Now, the next one is, okay, if I have x 0, that means I'm coming out here to x, right? That is the horizontal displacement, x, but I'm still at 0 in terms of my vertical displacement. Okay, 0 e to the x means I'm here, still at 0 in terms of my x measurement, but my vertical displacement is e to the x. And this, let's go ahead and let's do this the best that we can. Okay, and this right here, of course, is going to be x e to the x. Okay, well, you know, it's weird to look at these. It's weird to look at these two ordered pairs like they're actually on the Cartesian plane. And the thing is that they are. It's just that when things start to move, because it's e to the x and exponentials are really powerful, the height is going to get really tall really fast. Okay, but this right here, it should come as no surprise, is just x, and this right here is e to the x. So the area of this rectangle is simply x e to the x. Now, let's go ahead. If x increases at a rate of 1 unit per second, so given dx dt, it increases positive 1 units per second. The question I'm being asked is, at what rate is the area increasing? dA dt. Okay, and the conditional. Now, I'm going to ask you a quick question before we start evaluating. If x is at 10 units, what is e to the x at? Yeah, and that should make you think, wow, this is going to be a ridiculously large number. Okay, let's go ahead and differentiate, remembering that this needs the product rule. So I have dA dt is equal to x times e to the x dx dt plus dx dt being the derivative of x times e to the x. Well, both of those terms have an e to the x. They both have a dx dt, and what's left behind is x plus 1. Okay, let's go ahead. We have x, we have dx dt, right? Dx dt was our given, x is our conditional information, and if we're looking for dA dt at that particular instant, I can go ahead and plug in. If x is 10, then e to the x is e to the 10. dx dt is 1 unit per second, and x right here is 10 plus 1 units. And therefore, what I get is 11 e to the 10th units squared per second. And if you're wondering what that actually approximates to, it's 242,291.124 units squared per second. Yeah, really large, right? Okay, because basically it's whatever e to the 10th is, and then add another decimal because you're multiplying by a little more than 10, right? Add another digit. This has been us walking through and looking at related rates as they relate to two-dimensional geometry that is beyond the Pythagorean Theorem. Now, of course, we had a couple Pythagorean Theorem ones in there, one of them being cloaked, one of them being less so. And, of course, we had two area problems, which, of course, are Pythagorean Theorem in disguise. But we also had an equilateral triangle, we had a rectangle, we had two circles. We probably could have done a trapezoid problem. I just didn't run into one. Basically, these two-dimensional geometric formulas are set up and then differentiated, and it winds up being pretty straightforward, just as straightforward as the Pythagorean Theorem ones. If you have any questions, please do shoot me an email. Bye.